start writing it down, but you guys probably have that written down. Okay, total internal reflection. Bring this up here. Don't write the recall, all right? Don't write the recall. I'm saying recall, light bends towards the normal when the speed slows down in a new medium and bends away from the normal if it speeds up. We know that. Write starting from when. I'm going to have 3 pictures here. Describing different angles. Now, even though I did my demonstration looking like this, with the light coming down from the top, due to the fact that we see total internal reflection most often with light trying to come out of water, we normally draw the picture with the light coming up, just like yesterday's example. So remember yesterday's example where we had water to air, and we put the light coming up? The most common place that you see total internal reflection in the real world, and I'll give you examples of it, probably tomorrow when we're done the lab, is when we're going from something like water to air. So I'm going to just put here water and air, and I'm just going to write it down once. Yep. That's a situation that is, it's like a mirage, and that has to do, it is an example of it, but it has to do with the fact that there's hot air under cool air, and I'll talk more about those later on. So that is an example of total internal reflection, but when we get to the examples of it, which will be tomorrow, I'll talk more specifically of it. That's correct. But that's coming the other way around, and it has to do with not the water, it's more of the air itself. But you're correct. So what I want you to do here is, I've got air, I've got water, here's it is coming in, so there's theta 1. And which way is this thing going to bend? Away from the normal, so it's going to take off like that. Okay? And again here, this is our classic theta 2. We know how to do those calculations. We will be doing some of them today. And that was just the computer simulation of it. We already have it drawn in. What I'm demonstrating here, and it's automatically going to come up, if I increase the angle R, or the angle I, the angle R gets bigger still. So that's what this is. So I just have a larger theta 1. And then even bigger is theta 2, bending away. In my last picture, and you don't have to write air and water again, I think that's there. In my last picture, I've increased the angle so that the refracted ray travels right along there, right along the surface. In the experiment, you're going to see that if you're using a ray box that has white light, you'll actually see a rainbow at that point because it spreads the light out also at that point. With the laser, you won't see the rainbow because there's only one color in a laser. It's red. Yep. A very strong reflected ray. Yeah, that would be awesome because that's how we do the math. Theta 1 and theta 2 equals 90 degrees. Okay? And we could also call this theta 1 at this point theta C for the critical angle. It's the angle that results in this ray going right along the edge. At this point, we would also see a reflected ray. And not that we would do math with this, but we would have a theta little r. Remember our good old little r for reflection? That's what that would be. And it would be equal to the theta 1. It's a classic reflection. All right? I think next I have a definition. Come on, computer. What are you waiting for? Oh, it's bringing up all those things. Critical angle. And some teachers don't put this down, but I'm gonna put critical angle as theta c. So you could put it down as theta c, the critical angle. And it's an incident angle. It's a theta 1 that we want to calculate for if we want to find the critical angle. That's kind of neat. This only happens when light goes from a slow medium to a fast medium. You have the opportunity for this. And you have seen all kinds of examples of this. And tomorrow I will go over examples that you've probably seen in the past. You'll probably go, oh, I noticed that. That's pretty cool, right? Any angle greater than the critical angle will result in total internal reflection. And as a short form, you've probably noticed on my little board, TIR stands for total internal reflection. I've got it over there and I've got it over here. Yours is covered up. And now the T is gone because of my paper. This pen doesn't work. Anyway. If the angle is smaller than the critical angle, then the refracted ray will escape. It'll get out. And if the angle is the same as the critical angle, then that refracted ray is actually traveling right along the surface. And if it's made up of white light, it'll begin to spread out. Okay, let's calculate a few critical angles here. What is coming up here? All right. Calculating the critical angle. Now, in my next slides, I have all of these examples broken down into individuals. So just write down A, water, then I'm going to advance the slide and we'll calculate it. Don't write down A, B, C, D. We're going to come back to this to get some numbers. I don't know why that glass is animated like that. Doesn't matter. For total internal reflection to just take place, the angle of refraction must be 90 degrees. Use this information to determine the critical angle for the following. And then just put A, water. And what I'm going to do is I'm going to, well, we can remember what water's index of refraction is, 1.33. Zircon, we're going to need, I think it's 1.9. Acrylic, I think we're pretty good with it, it's 1.5. So, what do we need to write? If you didn't, don't worry about it. If you didn't, don't worry about it. All it states is that we need an angle of refraction of 90 degrees to find the critical angle. Okay? So, let's find the critical angle. We do this just like we did our problems yesterday. Draw a little picture of it. It's always air. But if it's air into water, that's fast to slow. It must be the light coming from the water going into the air. And that's why these are a little tricky. Because I could say to you, find the critical angle of water, and then I would have to tell you what the other medium is, air. But you need to know that I'm going to have my water down here, water, and my air up here. And because it's a critical angle, I must be going from slow to fast, which means my incident ray is down here. If this is a critical angle, where's the refracted ray? Where's the refracted ray? Kayla, what do you think? It's towards that's the normal, that's the surface. Correct. It's traveling along the surface. My light is starting in here, N1, N2. What was it for water? Tell me. 1.33. What is it for air? 1.00. Which angle is this down here? Sorry? It's theta C or angle 1, right? This is theta 1. Now, I'm not going to write in theta C because we don't have an equation that solves for theta C, but we know how to solve for theta 1. What's this angle in here? Yep. 90, and what is it in my equation? Theta 2. That's the whole trick into solving these problems. We want to solve for theta 1 such that theta 2 is 90 degrees. Okay? So now we do it the same way. N1 sine theta 1 equals N2 sine theta 2. Now you know what? When finding a critical angle, sine theta 2 is always 90 degrees. Because it has to be. What's the sine of 90 degrees? Just take sine 90. What is it? It's 1. Which means this value in here is always 1. Right? If we're going into air, what's N2? Jillian? It's 1. What's 1 times 1? 1. Which means for finding the critical angle for something in air, I'm going to have N1 sine theta 1 equals 1. That's always going to be true. I want to figure out the theta. Sine theta 1 is equal to 1 over N1, or 1 over the N of what we're trying to find. Then I need to take the inverse sine of that. Could you memorize that? Could you memorize something like sine theta C is equal to 1 over N1? I suppose you could. Do you have to? No. Because you can start with N1 sine theta 1 equals N2 sine theta 2. Yep. Sorry, say that again. No. These are just two variables that are multiplied together, but they're not stuck together. Yep. N1 sine theta 1 equals 1, right? Right? And you want to do this. You want to go, let's divide by N1 and divide by N1. How's this looking? Is that looking better for you? And then I want to go like this, right? Yeah. Because when you do that type of thing in a multiplication, you always end up simply taking it and putting it down on the other side. And as you go on in physics, you'll become very good at that step, so you don't have to write that little step down. But if you'd really like to write that down, you can. Or you could put the numbers in at any point in time. You could have put the numbers in. You could have put 90. You could have put 1. You could have put 1.33. I'm just telling you, this is almost like a little shortcut here. So let's do this question here for a moment. Sine theta c is 1 over 1.33. Sine theta c is equal to, what's that as a decimal? Yeah, Allison? 752. Therefore, theta c is equal to the inverse sine of 0.752. Allison, what do you got? 48.8 degrees. Okay? Did we all get 48.8 degrees? Still remember how to use our calculators? Now, let's do the same for acrylic. Yep.
Would you prefer us to start with the Snell's law, then rearrange it, or just go straight to shortcut?
That's fun, eh? That's a good question. The kind of the unwritten rule in physics. Let's say I was to give you an assignment. I would like you to start with this. You could then derive this by showing me these steps. And once you've done that, you could use that equation as many times as you'd like, as long as I see how you get that equation. Or, if you don't like that, you would show me from first principles. But in the kind of unwritten rule of physics, once you've derived it once, and as a teacher, I see that I know that you know how to get from there to there, you can use that equation. It's fair game. Yep?
We put in the numbers and then figure.
Yes, you can, by all means, if you absolutely hate this rearranging business. But if you're going to be the next Stephen Hawking, then you're going to have to learn how to rearrange some equations eventually. But you'll get practice in the future. Yeah. Like in the grade 11 and 12 physics, we're rearranging equations all the time. That's the way you do it. But you can start from first principles. You guys are just little baby physicists right now. Since we made the equation, let's start from here. Sine theta c is going to be 1 over, what's the N1 for our acrylic? Yep, 1.5, 1.50. So sine theta c, what's the decimal of that? If you're wondering the next two, I think it's zircon and diamond if you want to crash ahead. What do we got for a decimal? 667, and therefore theta c is the inverse sine of 0.667, and therefore the critical angle is what do you got, Kayla? 41.83, so we can stop at 41.8 is good. Notice what happens as the n gets bigger. What happens to the critical angle? It gets smaller, which means it takes less and less of an angle to keep the light in. Zircon and diamond, you don't have to write calculating the critical angle. We're just doing C and D. Does anybody remember the N for zircon? What did I say? 1.90, I think. 1.90. And diamond N is 2.42, right? And you're all good at your math. I'll just take the theta c when you're done doing all your steps. And if you come into the room without a calculator and we're working on calculators, you need to come to the front to get a calculator so that you can participate, unless you've got one. What do you got, Shane? 31.8 degrees. That's not very much, by the way, folks. Like, and you don't need to draw this, right? But if that's 45, we're talking about a little angle like that, right? If 45 is in that position, a little angle of 31 keeps the light in. What is it for diamond? Oh, that was a terrible equal sign. Then you're getting a decimal for the number and then inverse sign. What do you get?
24.
Now look at that, 24.4 degrees. Double that, that's 48. So again, if we think about that, if this is our surface of our diamond, and that's 45 degrees, 48, and then divide that by 2, that's actually not a very good representation of 31, but that is not bad representation of 24 degrees. What does that mean? That means any light that comes from this direction is going to be stuck inside the diamond. It's not going to make it out of the diamond. Light that comes in that little narrow wedge can get out. That's why diamonds shimmer the way they do. I'll talk about it more tomorrow. But when light enters a diamond, most of the light bounces around inside the diamond. Internally, there's light bouncing around inside a diamond. If a ray happens to come out at this angle, it then can escape, and it escapes at a very sharp angle because it's always very close to the surface. And if it's white light, as it escapes, you'll see here with the ray boxes, it spreads out into a rainbow. And so when that special someone comes in the room with their big diamond earrings on, the reason the diamonds sparkle with all kinds of colors, have you ever noticed a diamond, how they look very colorful almost? Different colors come out of the diamond. It has everything to do with the critical angle of the diamond. That's why they shimmer that way. All right? It has everything to do with physics. Just fun. Okay. We're not going to look at examples of total internal reflection. I'm going to stop the recording right now, and we're going to get ready to roll on to the experiment.